Okay, so welcome back to System Software. Last time we finished up looking at the file system and started looking at how to use system calls to directly use the kernel to operate our system. We saw a bunch of examples of file system calls like opening, reading, and writing files. And today we're going to look at processes. So there are three main things that the system provides you. They provide you a file system, provides you process management, and memory virtualization. Now you got to get memory virtualization for free if you just use Malloc. Malloc will do the system calls for you, and then you just use memory as usual in C. But first, let me see if there's any questions. Any questions from last time on system calls or logistics about the course? Anything on the projects? Oh yeah, hello is due today at a minute before midnight. Saw a couple of questions, but no real major questions. Any issues with? Yeah. Uh-huh. What editor did you use? Emacs?
I essentially followed exactly what it was saying.
And the script replay. It's probably fine. Let me know if you get a grade that you don't expect on it. I've asked the TA to grade like the next day, so he should be grading. You should have grades tomorrow if the TA runs it. Everything's automated for him, so he just hits a button. But yeah, let me know if you see anything wrong, and then come to office hours or let me know on EdStem. Any other questions? All right, let's do homework first, and then I'm going to wrap up the system call stuff because I didn't finish all of the system calls last time. I'll just show you examples of them. And then we'll move on, take attendance, and then move on to processes. So let's start with the homework. Okay, so let's look at number one. How can we tell whether two paths refer to the same file? Yeah.
Use stack to get its inode number.
Okay. Yeah, you can use the inode number. So now the path may have dot in it, may have dot in it. The paths themselves, even if it's referring to the exact same file name and in the same part of the file tree, you can just use the inode number to determine that. And also because of hard links, because you can refer to the same file in multiple directories with their given names, looking at the paths is not going to help you. But remember that in the Unix-style file systems, the actual file identifier, the actual file is this inode number. That's what refers to the data on disk. And the name, where does the name come from in the Unix-style file system? Where does a file get its name? Is it stored with the inode number? Is it stored on disk with the data in the file? Where is it stored? The file name. Yeah.
Is it stored in the directory table?
It's stored in the directory table. It's stored in a completely separate file from the actual data that stores your content. So if you have an MP3 file that has audio contents, the file system will manage how that's stored on disk, but the name of it is detached from that file. The name of it is in a completely different file called a directory file, which just maps names to directory inode numbers. So inode numbers are like phone numbers, and the file name is like, our names for phone numbers, like in a phone book. Okay, good. So yeah, just look at the inode number and you can tell whether two paths refer to the same file. Okay, so just some questions on system calls. What flag do you use to create a file if it doesn't exist already when you're opening it? What is it? O-create or O-creat, yeah. So just look at the documentation to find this. And yeah, sorry for the broken link in web courses. This link does work on my website, but not in web courses, so apologies for that. All right, if we try to open a file that doesn't exist, what happens? What we call open on a file that doesn't exist. What's that? It returns -1, yeah. The program doesn't stop. The program keeps running. It returns -1. And what do we do if we want our code to do something different if the file doesn't exist? What's that? Well, that's how you change the program, but let's say we wanted the program to do one thing when the file exists and a different thing when the file doesn't exist. What should we do? Yeah.
Wouldn't we add in a statement to just check?
Yeah, you just check. You check the return value. You do error checking. So, okay. What about a flag for truncating a file? Trunk, yeah, you just again, this is all just from the documentation. What happens if we, all right, so this one is a little more complicated. What happens if we open a file for writing, but it already exists, that file exists. We don't truncate it, but we write bytes to it. What's gonna happen, yeah?
It will overwrite the bytes.
It'll overwrite the bytes. Will it overwrite all of the bytes in the file? Let's say we have a file that's 100 bytes and we overwrite 10 bytes without truncating. What'll happen to those other 90 bytes, yeah? Yeah, the 90 will stay there. So it'll just overwrite those first 10 bytes. And then a question about writing a syscall that opens a file for hello for writing, creates if it doesn't exist, truncating if it does, and then error handling. This is just in the lecture notes. I think this is just already there. So creating it if it doesn't exist, truncating it if it does exist, and then, what did I say? Include error checking. So if it doesn't exist when we open it, then do error checking, although this should be exit failure. Yeah?
So when we run it with those three arguments, would it try to open with write only if it doesn't exist, and it would create, and then once it opens, and then regardless if it created or not, it would truncate it?
Yeah, well, truncating only matters if the file already exists. So it only applies if the file exists. Let's see what the actual documentation says. If the file already exists, that is a regular file. So it only applies in those conditions. Yeah. Oh, sorry about that. This is the mode. Yeah, I didn't explain this last time. This is the optional mode. This is these are the permissions. And there's a more elegant way to write the permissions, but yeah, I didn't go into this too much. We won't cover it this much here, but this is each of these octal words represents the user's permissions, the group's permissions, and the entire system's permissions. So this is just saying read write for me, read for my group, and no permissions for anyone else on the system. You can read the documentation for chmod, which means change mod, and it'll explain what those are. I forget why I had this in here. Maybe there was a default that yeah, I can't remember why I even had this in here. But yeah, I think it was just to override some default. All right, any other questions about homework? Syscalls? Yeah.
So at the end for question 5, will overwrite everything? Is that what we can say?
Truncate, yeah, truncate. So truncate will zero out the file, no matter how large it is. So if you have a 10 megabyte file and you open it for writing with truncate, it'll zero it out, and then if you only write 1 byte, yeah, the rest of that data is no longer accessible from that inode. So it'll still be on disk, potentially, depending on your file system. Yeah, so if let me go to the syscall notes. So I probably only mentioned this briefly when we talked about in file systems. When I talked about file systems, I can't remember if I mentioned this, but if this is a directory file, right? This is where files get their names. What does the delete command do? I think I didn't cover this actually. I probably covered it last semester. But how do we delete a file on disk? Or what are some ways to delete a file from your file system? What's that? RM is a tool. So could we implement RM? Yeah, you were going to say that. No, I thought you were. Anyone have a thought how you could remove a file? How would you implement RM? Well, that's how you use the tool. How would you write a program that would remove that file from disk? So we've got an inode number. So one way you could do it is you could open it for. Oh yeah, go ahead.
Just delete the entry from the table.
Okay, so one way is you just delete this entry. And now there's no way to access that file anymore. Another way is you could open it for truncating and tell the system to zero out the file. Another way is you could overwrite the file with all zeros. But the way remove works is it just deletes this entry. And then the system says, all right, well, this inode number is no longer being used anywhere, so I can reclaim it. I don't need that data on disk anymore. Yeah?
If we have a file with text and we want to add text to the file, is there a command set or do we have to?
Yeah, there's append.
Okay.
There's append. I think it's actually a flag. Yeah, it's a flag. It just moves the pointer into the file to the end of the file. Yeah.
It's like a question and then a question on top of that.
Yeah.
Is how does the recycling bin work? And then what happens if you delete recycling?
Okay, so good question. So let me cover deleting files on disk. So you have some physical medium that will store bytes. You can just flip bytes on and off, like a hard disk or an SSD drive. The amount of storage space is fixed and finite when that device is manufactured. And maybe they manufacture it so that it starts out with all 0 bits. When you create a file, the file system will store somewhere on that disk the bytes of your file. So if you have a text file saying hello world, the encoding of hello world in ASCII has got to be on that disk somewhere. If you just delete this entry from the directory file is a different file. So you've modified that file, but the original hello world file is still, the data is still on disk. Make sense? So if you want to you're not going to you could physically destroy the disk, and there's some fun talks, like DEF CON talks about destroying disks. But if you don't destroy the disk, that disk still has those bits flipped if you just delete this entry. You could zero them out first. There are techniques for even recovering data. But what the consequence is that most systems delete by just removing the entry because it's really fast, but your data is actually not gone. So if you're really worried about deleting something, if you just use RM, that data is still on disk. And it could be recovered by somebody who just, below the file system, grabs the actual hard drive itself and starts reading bits off of it. There are tools, forensic tools, for actually looking for data that is, say, image data or text data. So there are secure delete techniques that have to actually overwrite the file because you're not actually deleting the capacity for bits. You're just removing this entry or overwriting those bits that were there before. SSD drives are even harder because they, at the hardware level, they change where those bits are written. It's called wear leveling, so to avoid the same parts of the SSD being turned on and off all the time, which wears them out. Even when you do a delete, you may be writing to a different part of the physical medium. So recycling bin is nothing more than moving to another folder. There's literally a folder on your, so if you have a Mac or something, I think it's called .trash. When you do delete from the OS perspective, all it really does is doesn't delete it. It doesn't call RM, it calls move. And it just moves it to that folder, special folder.
So is it still in the hard drive or the SSD when you put it in the recycle?
Yeah, for sure. So it's just a different folder. So you just have a specially named folder called recycle bin, and instead of deleting it, it just moves it to the recycle bin.
So what if you delete it from the actual?
If you delete it from the recycling bin, well, yeah, so from the system, when you clear the recycling bin, it's deleting the entries from the recycling bin's directory entry. But it's not doing a secure delete in most systems that I'm aware of. That data will still be on disk, it just won't be referenced in any directory, from any directory.
So, sorry, I just have a lot of questions about this.
All right, yeah.
So if that's the case, then how do you actually, is uninstalling the same thing? How does it work?
No, you have to physically overwrite the data on disk.
Okay.
You have to physically overwrite that data on disk or destroy the disk. Because even for hard drives, if you overwrite data, apparently, I'm not an expert in this, but apparently there's some magnetic residue of those bits. So there are some techniques where they can actually collect. So some people are shaking their head. You can actually still, even if you overwrite with all zeros. So there are tools that will just overwrite over and over and over again, overwrite with zeros or random data to the disk. The best way is just destroy the disk, physically destroy it. Is probably the best way if you actually want to delete something. Because file system delete is just, let me remove that mapping from the name to the inode number from the disk. And then eventually, as you use the disk, that data will be considered free, just like in malloc, when you have free memory or allocated memory, eventually the data that was associated with that inode number will be overwritten by other files eventually. So you could also just fill up the disk with like random data over and over and over again. SSDs are a little harder because with this wear leveling. Anyway, a little deep dive on so if if you understand how the system works, how file systems work, you can realize the forensic consequences of what deleting means. So yeah, deleting is like fake. It's just deleting from the file system this tree, but it's not actually deleting the disk because your disk has a fixed number of bits that it can store. That's fixed from the factory. That's not going to change when you run RM. Okay, so that's deleting. I think I didn't cover that last time, but it's a kind of important thing to know about your file system, especially if you have stuff you want to actually delete, data you want to delete. All right, other questions on? Were there other questions over here that were after the delete stuff? Okay. Okay, so that's file systems. Let me also quickly finish up the system calls that I covered because there's one additional system call that we'll need for our project, and I just want to show that to you. So we did stat, which you're going to need for the project, reading, which you'll need for the project, write you won't need. So read is pretty straightforward. If you remember, once you open the file, you get a file descriptor. You need to allocate some buffer of some size. And then read is just give the file descriptor, give it that byte buffer to store data in, and then give the number of bytes you hope to read. So if I have a buffer size of 10, the return value is the number of bytes that were actually read. Will the number of bytes actually read always match the buffer size that I give it? No. Why? Why not? What cases where will it not? Like if I ask it for 10 bytes from the file, when will it give me less than 10 bytes? Yeah. If there aren't 10 bytes in the file, that's one. Any other cases? If it gets interrupted, yeah. The kernel is interrupted, it may just stop reading, return to you, and it'll tell you how many bytes were read. So you as the developer need to write code that anticipates that happening. For the small files that we're going to be using, you're probably not going to get an interrupt. I don't even know how to construct a case to make this happen. I'm sure it's doable, but you could it would have to happen in a really specific timing. Okay, writing files we looked at. It's a little complicated, but take a look at the code. And then directory operations. You won't need writing for the project, but directory operations you will. So they're just a little bit onerous to use. Just like with files, you open the directory, so open dir the path, and do some error checking. You get this pointer to a directory struct. And then this is the code that will read each entry from that directory. You just call read dir over and over and over on that directory pointer. And every time you call read dir, it'll give you the next entry. It's like an iterator if you ever saw like Java or C#. You just keep calling read dir on it, and it'll give you the next entry until it gives you null, and then you know that you're done reading. And this read dir gives you a struct that has information about that file in it, like its name, and you can use that to print it out, construct new paths, etc. Questions on this code? So it's just open, and then while read dir. Is anyone expecting this to be a double equals, or why is this a single equals instead of a double equals? This is a C language trick. So this is an assignment statement. So if you've ever accidentally did a single equals when you're trying to do double equals, this is why the compiler didn't yell at you. So this is the same thing as running this statement first, and then just putting cur dir here. So it just takes the result of cur dir and passes that as the value to this while loop. Questions on this? So basically, you should be able to do the whole project with just these example snippets of code, I think. I tried it myself yesterday, and I think I only needed to use this code and string processing stuff, which I assume you know how to do already. One thing I want to point out about these directory operations, these are actually not system calls. If you look at the actual system calls for getting where is this? If you look at the system call for reading directories, the manual tells you this is not what you're interested in. It says don't use this because these are system specific. There apparently are no standard system calls, I think, for directories, or at least the data structure returned is, if you're on Linux or Mac, BSD, you might get different data structures, so standard practice is to use the library call, which calls the system call. And I've given you the documentation here so you can see the structure of the directory entry that you get back. So here's the name. The name is all you're going to need for our project. Questions so far on that system call? Okay. All right, let me show you the project as well. So the project is up now. So you'll be implementing a tool called myFind. So find, I'll probably show it a little bit today, but find will just basically list out an entire project tree. So if I am in, let's go to Eustace. So if I'm in the user include directory, for instance, and I type find, without any other options, it's just going to print out every file in your subtree, in your current directory subtree. So it's just going to print out every file in your subtree. So you're going to write a tool like that, which is going to use file system operations, directory reading operations, to list out all the files. And it's also going to work like the WC command. WC will take a file and give you the number of lines. Actually, it'll give you the number of lines, words, and characters. -L for lines, it'll just give you the number of lines. So you'll be writing a tool that will list all of the files in a directory and also optionally print out the number of lines in each of those files. Questions on the project? So it's a combination of these two things. So you'll be working with directories, you'll be reading files, and opening and reading files. That's it. So here's what the input is supposed to look like. This is kind of a classic way in the Unix style world of describing interfaces. So this should be the name of the program. It must be myFind. And then these square brackets mean optional. So the -L option may be there or it doesn't have to be there. And then a path. So here's some examples of using it. I could say myFind and then this path here, dir file subdir /file. Or I could put the -L command, a -L option before the path. Questions on the interface? Pretty simple, right? One or two arguments. If there's two arguments, this one must be -L, and then the second one should be a path. I've also listed out the error cases, so if there's no arguments to the program, there's two arguments, but they aren't the -L flag. And if you get any other system call errors when trying to open and read directories or files, then just skip that file. Here's an example. So I've constructed a file tree that looks like this. It's called contents, and then it has one subdirectory. That subdirectory has a file, and contents has two files. So if I use the -L option, it will list the number of lines in each file just for regular files. So directory files, they're not like readable by the user. So you don't have to print anything out, but just for regular files, print out the number of lines. Questions on this program? So just a little exercise in writing a kind of system type software. I've given you the exact format strings to use, so there's no mismatches in the output. So these are the exact format strings you use. With -L, it's a string followed by a tab character followed by a long integer. But if you just use these format strings for anything that's being printed out by the program, then it should match our automated test cases. This lists out where to find references of the system calls. You can also look in the lecture notes for examples and readings for them. I've also given you some code for joining paths. So when you use that directory read directory, it's not going to give you the full path. It's just going to give you the directory entry. So it's just going to give you this name. If this is a file you want to open for reading and it's in some nested directory, having the name is not going to help you find that file. You need the whole path. So you need a path up to that point plus this file. You're going to need to concatenate paths together. So I've given you some code to do that here. And also some automated grading scripts. So my, if I didn't mention it before, I tell you what all the tests are, but then I give you half of them. Otherwise, it's like way too easy, I think. So I give you all the odd-numbered ones, and the even-numbered ones, I describe to you what our test is going to do. Follow these directions here. You can you can just download them and unpack them, untar them from the command line. And these are instructions on how to run those automated tests. All right, let me quickly show you what this looks like. So here's the FS project. Here, if I use the tree command to show you the directory structure that I'm going to use my find command on, if I run my find, oops, see, it tells me invalid number of arguments. Forgot to put the argument there. Oops, I have debugging output, which is going to, so it'll literally concatenate with the /. That's not going to hurt anything. All my tests will not use that. We'll use that /. So anyway, so this is what the file tree looks like with my tree command, and this is my implementation of my find, where it prints out every file except for the dot and dot files. This is described in the project description. It'll print them out. Questions on that? Pretty straightforward, right? You just list out, you recursively go through the subtree and print out all the files in it. -L will do the same thing, except if it's a regular file, then we print the number of lines. How can we tell if a file is a regular file? Is there a system call that will help us do this? The stat system call that we looked at last time, the stat system call will tell you type of file. And so just look for the code there. It'll show you the code in class for the stat command. This shows you code on how to get the file type. So regular versus directory versus any other file type. All right, questions on FS project or syscalls or the file system? Yeah.
Do you care how we call it recursively, or like what order it goes?
Oh yeah, the order doesn't matter. So the scripts will sort all the results first. So the order won't matter. And the order could also depend on the order of the directory table. It could even be system dependent potentially. So yeah, order doesn't matter in the output, and that's accounted for in the scripts. Let's see, do I have the test scripts here? Oops. So here's how you call. Okay, because it's using the same directory structure. I deleted it. So yeah, this is what it'll look like when you call it. So it'll tell you success or failure. 0 means success, non-zero means failure. Not very informative, but it'll, if you have debugging output in your program, it will, you can use this to tell you whether you got it right or wrong. You can open up this test file, and it'll show you, the ground truth here, and also the command that's being run, and the set of commands that are being used to create the directory structure. So you can use that to help recreate and debug your test. All right, any other questions on file system project, file system, syscalls? All right, hope this is a fun exercise. It was fun for me to do yesterday, unless system stuff is not your cup of tea. but hopefully it'll at least be informative. But yeah, so all of the system calls in this syscall lecture, you can really just cobble those together to put together this program. Look over the project description. I didn't cover everything in here. I actually give you like the algorithm, the recursive algorithm, and some other information. So make sure you read over this description. And yeah, so it's going to be due in 2 weeks, I think. What is it, 2 weeks or 3 weeks? 3 weeks for this. Okay, there's no other questions, then let's do attendance. Okay, so let's learn about processes. So we finished up file system and started looking at syscalls for actually working with the file system directly through the kernel's API. And today we're going to talk about the process abstraction. So what is a process? A process is just a running program. All right. So I'm missing my pen, so I don't think I can do any diagrams, unfortunately. I thought there were no diagrams here, but well, I can show you on disk here. So I've got my, let's do my hello project. So when I compile my program, I've got my C program, and that's stored on disk. The bit representation of this is stored on disk through my file system. And when I compile it, I get this hello binary. And if we try to look at it, it's not going to look like my C program very much. What's in this hello executable? Is it C code? When I run GCC to generate the executable, is that C code that I get out of it? No, what is it? What's that? Yeah, on this system, it's x86 machine code. So that's what the processor will actually consume and run. That's what you actually pass the processor and consume and run. But at this point, this hello program, it's just a file on disk. Once it's loaded into memory and the processor starts running it, that's when the program becomes a process. Questions on that? So a process is just a program that's currently running. And now you might think, well, it's not that hard to do if you have a machine already and you have some machine code. Well, you can write a little assembly to, I think everyone took computer architecture or computer organization, right? So you just point the program counter at the beginning of your program, put it in memory, point the program, and just start running it, right? But what if we have multiple programs to run and only one CPU? So most of us, we might have multi-core devices, but if we want to run 100 programs and we only have 1 core or 8 cores, how can we run those multiple programs? Or how would you do it? So you have one processor and you want to run 10 programs. What's one way you can run 10 programs? What's that? You split the load? Okay, so what's an easy way to split the load? Yeah.
CPU virtualization.
Well, yeah, that's what they're going to do. Yeah, CPU virtualization. What does that mean? How does it work? Well, one thing we can do is we can just run one program at a time, right? Just run them in batch. But if you want to be able to watch your cat videos and do your programming assignment at the same time, and you want it all to work at the same time, we need to do something more clever than just running one program at a time. And so the technique that emerged decades ago for allowing the illusion of multiple programs running is called time sharing. And this is where your colleague mentioned CPU virtualization. We virtualize the CPU. So we give programs the illusion that they have exclusive access to a single CPU. And then what the operating system does, the operating system will quickly switch between these programs so that each program thinks that it's running on a single CPU, but the operating system is quickly switching between each program. So, your cat video is playing in the background, your browser is running, and it has a sequence of code that's executing. It may execute 10 instructions, and then your editor for your programming language, for your programming assignment. That's going to run 10 instructions, and the operator is going to switch back to the browser, switch to your IDE. And when you actually use your machine, you don't feel this at all, right? It feels like they're running at the same time. But these processors are running so quickly, and the operating system is switching between them so quickly, that you have the illusion that they're all running at the same time. It's kind of like animation. You know, animation is individual frames of cartoons, and by running them really fast, it looks like movement. So kind of a similar idea here, where each of those programs is freezing really briefly, you know, for a fraction of a second, over and over and over again through that second, giving you the illusion that they're running quickly. Yeah?
If you have, for example, a game where you have a million objects that each have a boatload of code, would it at that point, when you start getting to that level of intensity, start to become noticeable at all?
Oh yeah. I mean, you can notice this even if you just like open up lots of tabs in your browser. Now, part of this is not necessarily the processor. This might be the memory usage. But for sure, if you're doing something really compute intensive for the CPU, then you will notice it. You'll notice a slowdown. Or if you have any real-time requirements, you'll notice a slowdown for sure. Now, modern, you know, gaming consoles and modern devices, they don't just have one CPU. They have a CPU that has multiple cores and techniques for literally, you know, running some instructions at the same time. They have a GPU, which is an entirely separate chip, which can run operations separate from the CPU. But for all of these cases, if you want to run more programs, run more processes than you have cores, have processors, if you want the appearance of real time, then time sharing is the way it's implemented on your device. You're just quickly switching between these programs. Who's heard of this concept before? Interesting. In computer organization, they didn't talk about this, time sharing. And so just like with the file system, where you don't have direct access to this, you know, giant string of bytes that you can read and write on your disk, when you run programs, you don't have control over what the processor is actually running. Instead, you ask the kernel, you ask the operating system and say, hey, I'd like to run this program, and it gives that program the illusion that it has exclusive control over the processor. So you as the programmer write your program pretending that you're the only program running on that CPU. So in the same way that with the file system, you write as if you're reading and writing files, but the operating system will manage how that actually gets distributed on your hard drive. Yeah.
So if that's the case, is it all possible for someone to tell the kernel, hey, I want to run this, and the kernel just goes down?
I mean, yeah, for sure. So there are limits on the number of processes that can run at the same time. There's like a soft-coded limit. And so if you exceed that, the processor will just say no. And looking at the file system case, where the kernel can say no, how might you think the kernel will communicate that to you when you try to run a process? So how do you access files for the kernel? How do you say open a new file with the kernel, with the operating system? That's what we learned about last time. You do a system call, right? There's a system call, an open system call. Well, we'll see system calls for running and managing running programs. And just like with every system call, there are error cases, and the kernel just might say no. Now, the limits on, like, if you have a modern drive or a modern machine and you're running hundreds of programs, the kernel is probably not going to tell you no. Instead, what's more likely is that the kernel will run them, but you're more likely to actually run out of memory before you're going to run out of processor stuff, unless you're doing, you know, intensive gaming or math operations. So yeah, but yes, the kernel will absolutely tell you no. Yeah.
Sorry, not a weird question. So if in the example you gave, we run 10 from one program commands and then 10 from another and then 10 from another, does that at all introduce security risk where if you have access to a system?
Absolutely.
You can command from that?
Yeah, so anytime you share resources and you have this definition of what this abstraction is supposed to do, so the abstraction is supposed to isolate each program from each other. So in addition to slicing time for the processor, the kernel will enforce that each of these programs can't touch other programs, that they're isolated. But there are some famous examples like the Spectre and Meltdown attacks, where they use side channels to read information from other programs. So absolutely, you have this risk when you have shared resources and you claim some security property like isolation. So yeah, for sure. Yeah, okay, so that's time sharing. And the way modern kernels implement this is, which was developed not just in Unix, but in prior operating systems, is to have this process abstraction. So just like the file abstraction, that file tree is not actually literally on disk. It's implemented through this, say, directory files. Here we have this illusion of a single process running on your CPU, and then the kernel is what provides the illusion for you. You just interact with the kernel, and it'll manage how those programs will be time shared on the underlying program. All right, so the way this works is the kernel will freeze the state of a process while another process is running. So if we have 10 programs running on our processor, the kernel will actually take all of the information about that program, like what registers, values it has, where the program counter is in the program, its current memory, and it'll freeze that. It'll copy that in memory, and it'll hold on to that while it introduces another program, while the other program runs. Then when that program gets frozen, its registers, its program counter, that'll all be saved into the kernel's memory. And then the previous program, all that stuff will be copied back into the processor and into memory effectively. Oops. So the tool for this is called a process control block, and it's just a struct. You know, if you opened up like I can actually find an illustration of this. You can actually see documentation of this. I put a link in the notes if you want to see what this looks like. But you can actually see what the structures are for this, and the details of this. If you want to see this for say, Linux, it'll go into details of this. The reading will also go into this as well. But it's just code. So there's literally a struct. There's literally a struct that says, you know, here's register A, here's register B, here's the value of these. And all that will be saved for that process while another process is running. And the kernel is literally just copying this data, saving it, and then copying it back when the process is meant to be run again. Questions on this? So we kind of simulate multiple processes running by saving and restoring their state really, really fast, several times a second for these processes. All right, questions so far on the process abstraction? Processes, yeah.
So this is happening like multiple times a second?
Oh yeah, many times a second. So the what's it called? The time delta or something is very small, like milliseconds or hundreds of milliseconds, I think. I don't know what it is. Depends on your system. So this is something you can actually configure if you wanted to. So for like high performance computing, you know, if you have people are doing, say, you know, climate models or scientific computing, they may be running one program for a long time, and so they may configure their system to not switch very quickly, so that they have some more dedicated systems. For our consumer devices, we usually expect like interactivity, responsiveness, and so you'll have a much smaller time delta that you switch at. So it's based on time. So the processor has a special chip that's a clock that'll send signals to the chip, and after a certain amount of time, it'll call an interrupt, and then the kernel will take over, switch out the process really quickly, and then resume running another process. Yeah?
Is this kind of like what the priority in Windows is? When you give like a certain application priority or another one?
Exactly, yeah. It's related to that, yeah. Yeah, so the part of the kernel that manages this is called the scheduler, which decides on which processes to run. And on some systems, you can tell the kernel, I want this process to have a different priority than other processes. I think it's sometimes called the nice value in Linux. So yeah, and I mean, there's a whole bunch of literature and work on different scheduling algorithms that work better in different scenarios. You know, if it's a windowing interface versus command line interface versus a web server, there's a lot of decisions about how you optimally do scheduling. Yeah.
Is it the same as, like, is this running 3 hertz? Like, it doesn't, like, on the CPU?
I mean, yeah, in a sense, because if you can run commands faster, run instructions faster, then in the same time delta between processes, you can get more done on that program in the same amount of time. So yeah, if you have a faster processor, then you can have the illusion of more responsiveness, because you can either run more processes in the same amount of time, or run the same processes further along in the same amount of time. So for sure, yeah, because hertz is what? It's over time, right? It's like rate over time. And usually these, at least for like Linux, consumer Linux, there's a time delta that's used to decide when to reschedule processes, rather than an instruction delta. So my example of run 10 instructions was a little artificial, because it's really like run for 10 milliseconds and then switch. All right, other questions? Other questions on this? Yeah.
Just to clarify, so a reason like your program gets slow, you have a bunch of stuff running, just because there's so many other programs to try to support this faster thing?
So the question was, is that why your program's running slow? That's one reason. So, you know, the main components of your hardware are your memory, your processor, and your disk, and also your I/O. So if your program is bound, you know, so-called CPU bound, that is, it needs a lot of CPU relative to memory, then that could be the reason. But at least when I'm running programs, usually it's like memory is the problem, memory pressure. You know, if each of your processes is asking for 10 gigabytes of space, you know, it's like editing a giant video or something, and you have hundreds of those, then it could just be memory pressure. It could be because the memory is also shared. This is something I'm not really going to cover in this course, take an operating system course, and they'll talk about how physical RAM is shared between multiple programs, like why you can say watch a 20 gig video, even though you only have 8 gigs of RAM, and you're also like, you know, programming and browsing the web. That RAM stick is also being shared and virtualized by the operating system. But the interface to that is invisible to you, basically. That's basically malloc and just using variables in C. Okay. Thought there was one other thing I wanted to say, but I forgot what it was. Any other questions on the process abstraction? All right, so that's the process abstraction, and it's just like the file system, the operating system gives you the illusion of a single processor that you have available to you. All right, so let's look at how the system call, how the API is for this, how the interface is to using processes in the Unix world. And this is standardized at this point in most major operating systems. So the way this works in the Unix world is there isn't just one instruction to make a new process. There's two. And so it works a little bit like, you know, cell division. So the first instruction is called fork, and what it does is it copies a process. It's like cell division. It takes a currently running process and it copies it. And this may sound a little silly because, well, why do I want, you know, if I'm running find, I don't want to run something else. Why do I want two versions of that program running, identical programs that are running? Seems a little weird. But then there's another call called exec, which replaces the program code of your process. So remember, the process is a running program, and a process is just the program in memory, and then, you know, the program counter where it's being run. And if you want to make a new running program, that's a different running program, you have to use two instructions, fork and exec. Okay, thoughts about this? Questions about this? Maybe think like, why would you want to separate this? Yeah.
If we run fork first, then the process already exists.
What if you run? Wait a second.
It says that it copies the existing process with fork.
Yeah.
And this is to start a new process?
This is to start a new
So
process.
the process is already running?
The process is already running, right? Little problem, right? So if you need an already running process, how could you ever make one, right? If you don't have a running process. No, because exec only replaces an existing process's code with a new program. So the problem here is, well, one problem you can think of is, what about the initial process? Where does this initial process come from? So this depends kind of on the system, but there's, you know, on Linux or Unix type systems, there's an initial process, usually called init. There may be there's other variations of this. But basically, when your machine boots and your operating system boots, at that time, the initial process is created when you boot your program. And depending on your initialization scripts, it will start up, say, a login prompt. So when you see like a login prompt on your system, that's a program that's running, that somebody ran. So let me show you what this looks like on a real system. Let's look at this. So there's a command called PS tree for process tree. And you can see, well, the init program here is called systemd. So historically, this process was called init, but there's been new tools for managing system processes, and these are very system dependent. But this one on this system is called systemd. And so this program was run basically by the bootloader when your system boots up. Part of that process is to initiate the very first process of your system. And then all other processes that are running, when you run bash, when you run find, when you run ls, all those are actually descendants of this single initial process. So the way, let's take a look here. So somewhere down here is a program called SSHD. This is effectively the login program. So when you call SSH, that's a client that will log in to use this. So eventually, it's actually a child of systemd. So the systemd process, as part of its startup, there's some scripts that the sysadmin configures here, says, all right, I want to run the SSHD program after systemd is created. And let's see if I can actually find my So these are all sorts of different users here. We can actually see what other users are running. I don't know which one is mine, but once SSD is running and you log in, SSHD will create a new process for your bash command line. So bash is yet another program, that command line you're interacting with. That's just another program that reads in commands and performs tasks for you. So SSHD will fork a process that then runs the bash program. And then, for instance, if you're using Emacs, bash will fork a process to run Emacs for you. And so you get this tree structure to run your processes. And all running programs are descendants from this initial process. Sort of makes sense? So this is why you can do this kind of very sophisticated process management with just two system calls. Just a system call to create a new process and a system call to change what program that process is running. So for each of these new processes that are running, these new programs that are running, init or systemd was forked, and then its program was replaced with the SSHD program. When you logged in, that SSHD process was forked and then replaced with the bash program. When in bash, when you typed in the word Emacs, under the hood, it forked a new process and then replaced that running process with the Emacs program. And you're actually going to write a little shell interpreter, I think, as part of this class to see how that process actually works. Okay, so that's the Unix style process management abstraction and API. Questions on this? Questions on this so far? So we'll actually work with it. We'll actually do the syscalls and work with it. So don't worry if it's a little abstract at this point. We'll actually write system calls and actually do this. But all right, so let me show you in Bash. And Bash has a lot of process management stuff built in, and there are a lot of tools built in for working with processes. So let me give you another little command line crash course for working with processes on your system. And this is part of the reason why the command line is like a powerful interface to know, because you have a lot of low-level direct access to your kernel, to your operating system. So you can work with the file system abstraction. You can work with processes in a very fine-grained way. All right, so the first thing we can do is we can run PS for process to view what programs are running in this current session. So this is basically children of Bash. So Bash, this is the program that I'm running now. And so you can see I just have two, my Bash program and PS itself. You don't necessarily have to know all of the command, the options to this, but I'll just show you a few canned ones that I use. If you ever want to see more on the options to PS, you can use the man page. But I just memorize, I memorize some pre-made ones. So PSAUX, this will show you all processes that are running on the entire system. So you can see here, here's the user. So we can basically see other users' programs that are running. So I don't think this is private information, but root, this is the root user. I can find myself on here. So you can see I'm running these two programs on here, running SSHD and bash. So that's all processes on the whole system. And we can view this as a tree with this command. So this is kind of like PS tree. This is the same thing we saw before, but you can kind of see the tree structure here, where here's SSHD forked from systemd. Here's bash being forked from SSHD, and here's PS being forked from bash. All right, so that's the PS tool. If we want to run a process in bash, it's really simple. We just type the name of a program that exists on our system and hit enter. And under the hood, bash is running fork to create a new process, and it's looking at the LS, the executable program itself, loading it into memory, and then running it in that new process. So what's a little unusual about this is when I run ls, when I run fork, there are now two versions of bash running at the same time. The exact same programs running at the same time. But once I run exec, that process is, a program is being replaced. It's kind of like, you fork a new cell and then they're identical, and then you replace the DNA of that cell with exec. You replace it with a new program to run. So this is kind of a convention in Unix to have command line arguments. These command line arguments are automatically passed to argv for you by the kernel. The kernel is taking all the text on the command line after the command, like this, and it's passing it into argv in main. That's part of the system toolchain. We'll look at that a little more when we learn how programs are actually loaded and run on the system. So the reason we can type ls, even though there's no program called ls in our current path, is because there's environment variables. These are kind of system-wide settings that that store information that programs can use. There's actually, in addition to argv, there's another argument to main that gives you access to these environment variables. Usually they're not shown in like C programs, but there's this list of paths that I've told bash have programs that I can run. So this ls program, if we want to see where bash thinks this ls program is, we can run which to tell us the full path, the full absolute path of that program. And why would you want to do this? So I have a program called hello here, and I can't run it here. Why might we want to design it this way, where we can only run programs that are in well-defined set of paths instead of anywhere in our current directory? Why would the system designers want to have this style where I can't just run hello? And this probably annoyed you a lot, right? Like you built your program and then you tried to run it and it said, I don't know where that program is, but it's like, it's right here. It's right here in my directory. Why might you, and then what do you have to do in order to run the program? You have to do // right? You have to do / the program. Basically, you have to give a path to it instead of just the name of it. This is just a man-made design. This is not some computer science truth. This is really just to, if I have compiled the program called ls in my current program, bash would run that instead of the kind of official one. Could be like a security problem, right? If you allow running any programs in any current directory. Anyway, so where bash, like this is just a convention for bash. Bash looks at this path environment variable to search for programs to run, search for commands to run. Whoops. And you can see where bash resolves that program with which. So I put this on here already. Say again?
You compile a program that's outside of the directory from that?
Yeah, you can compile a program somewhere else. Yeah, for sure. Yeah, so there are some commands in bash that are not programs. So if I type which cd, if I just put a random program here, it's not going to give me anything. CD is built in, so it's a command that bash itself interprets. And we'll see this again when we actually build a version of bash for ourselves. So then a little quiz. If I do have a program named CD, how do I run it in bash? Yeah, /cd. Yeah, exactly. Or give the path to it. And yeah, you can run programs in other just by its path. Okay, so let's talk about one of the other innovations of the Unix operating system called standard I/O. Who's heard of standard I/O? Okay, everyone, right? Where did you hear? In what context did you hear about standard I/O? Anyone wants to say? What's that? Standard input and output, right? So if I run printf, where does its output go? It goes to the terminal. Okay. Any other answers? So it does, right? If you run a program, you run printf, and you run it, it goes to the terminal. But actually, under the hood, where it's really going is the standard out. So this is like the implementation of printf. Under the hood, it's going to this file called standard out. But where is this file, and where does it come from? So the reason standard out works, the reason standard I/O works, is that when the Unix kernel creates a new process, by convention, it gives you 3 files that are already open. So normally when you write to a file, you call open, and you get this file descriptor, right? But when you create a new process, the convention in the Unix world is to already have open 3 files for you. And these 3 files are called standard in, standard out, and standard error. And so if you read this is in the standard I/O man page, it says, at startup, 3 text streams are predefined and need not be opened explicitly. Standard in, standard out, standard error. And so the reason printf works is not because it goes to your terminal. It works because the Unix convention is that whenever you have a new process, including your Hello World program, the system will ensure that those 3 standard I/O files are already open for you. So the question is, why do this? Why not just have the developer can say, hey, I want to print out to the terminal, right? Why do this at all? Why do you think? Why do you think you would have this design where you, by convention, just always open 3 files? You may not even need standard in, right, in your program. Why bother always opening these 3? What's that? Okay, it's standardized. Standardized is what? Standardized the I/O, right? Standardized the I/O. So when you write your Hello World program and you write printf, you don't have to worry about where the terminal is, for instance, right? So maybe it's like a windowing system, or maybe it's coming out a different type of console, or maybe the file for the console output is a different number or a different name. So by doing this, programmers can abstract away decisions about I/O. They can just assume that there's already an input and an output to their program. And if you want to rewrite your program to not be a terminal program, but to instead write to a file, you don't have to change your program at all. You can just, the person or the tool running the program can change where I/O goes. You see what I'm saying? So you don't have to go recompile your whole program if you want to change what your I/O is going to be for your program. So let me show you an example of this on the command line. There's a useful program, a very simple and useful program called Echo. And if I look at it, it's actually a program that was written. It says display a line of text. It doesn't even go into details of it, but what Echo does is it takes your command line argument, like hello world, and it writes it to standard out. So this program is super, super simple. I can even show you what this program looks like. So this is pretty much all you need to write the program Echo. You just take whatever the argument is, and you call printf on it. Pretty simple, right? You just take the arguments and call printf. That's all echo does. But because I have this standard I/O convention, and I'm using printf to go to standard out, right? Because that's what actually it goes under the hood. Whoever's running my program can change where the input and output comes from and goes to. So in Bash, there's syntax for changing I/O. So who's ever seen this like little caret, this little angle bracket? Okay, not many people. So what angle bracket says is change standard out to be a file. So if I use angle bracket and then a file name, notice there's no output to my terminal anymore. So this is why I kind of said, printf does not print to the terminal. It prints to standard out. And because it prints to standard out, I don't have to go in and change echo here to I don't have to open a file and then ask the user for a file to write to. All I have to do is write to standard out. And by abstracting away decisions about I/O, that means whatever system is running my program, is using my program, that's where the decisions about I/O can be made. So now I've got this new file called this is the output. And in that file is going to be the output of hello. So how can I print it out? I can use cat to print it out. And there it is. There's the output that echo made. Make sense? Questions on this? So it's subtle, but yeah. In Bash, it'll overwrite it. It'll overwrite the file. So be careful with doing this. It'll open and truncate and overwrite the file. It'll open and truncate. Yeah. So this is what Bash does. What this means is that you, as if someone you are building a system, you don't have to write one giant program for everything that you want to do. You can use programs as components and then alter their I/O to make a larger system. So let me start. So let me highlight that, since we only have a few minutes. Let me highlight that notion of constructing larger programs. And I'll go over this again next time, but the Unix philosophy kind of introduced this notion of kind of Lego blocks, programs as Lego blocks that you can put together to make larger and larger programs. And this abstraction of standard I/O is one important piece of this. So there's this, this is the Unix philosophy kind of from the kind of old documents on Unix. So one is make each program do one thing well. So that's like a Lego block. You have find, which just lists out everything in a subtree. You have WC, which counts stuff. You don't need to put this in one program. And number two, expect the output of every program to become the input of another, maybe unknown program. So this is what standard I/O enables. It enables you to link multiple programs together. So let me just show you a quick example. Let's say I wanted to search for a specific file. I wanted to search for the standard IO.h. Well, if I have a program that lists every file in my subtree, and I have a program that can find instances of text, so if I type standard IO here, it'll highlight that instance of text. I can combine these two programs. And I'll talk more about it next time, how to combine them. But I can take these two programs, and through this standard I/O, I can join them into effectively a single system or a single program. And now I have a tool, without writing any new C code, I have a tool that will find files by file name, by just combining two well-defined tools and using standard I/O. Okay, so it's 1:15. I'll actually show how to do this in Bash on the command line, and then we'll actually build a Bash-like tool that will make this kind of Unix-style Lego block building possible. All right, everyone. See you next time. Have a good weekend.